Welcome back to our Queensland Year 12 Physics Syllabus, Unit 3. We are following the work of the textbook by Walding. We're looking at Chapter 2.1, Forces Due to Gravity. That's an interactive activity to get students thinking about what we're doing today. Let's look at what our learning intentions are. We're going to look at weight, normal force, applied force, friction, and success criteria. We're going to be able to do calculations involving these terms, simple calculations. Okay, when we look at the forces acting on an object, we generally categorize it in four different forces. We have gravitational force, electromagnetic force, weak nuclear forces, and strong nuclear forces. And all the forces acting on an object are going to be one of those forces or a combination of those forces. In this part of our work, we're pretty much looking at this one at the top here, and we'll start to look at some of those other ones as we get further into Unit 3 and 4. We should also think in terms of the forces that we put on an object is an applied force. It's a force that's acting on an object, but there can be multiple forces acting on an object. And when we do the sort of the vector analysis of all of that stuff, we can work out what the net force is and the net direction that an object is being forced. At the top corner there, we've got some pictures from the original Simpsons episode. All right, weight versus mass. This should be revision for you. Mass is a measurement of how much matter is inside an object. It's measured in kilograms, but it's how much stuff is inside that makes up that object. Weight, on the other hand, is a force of gravity. It's the gravitational attraction between an object and Earth. We think of it in terms of G, because G is our constant that we calculate, and it's based on the mass of the Earth and the mass of the object being attracted. Usually, if it's us being attracted to Earth, our mass is insignificant compared to Earth, but we can work out the mass of the Earth, we can work out the mass of other planets in this solar system, of planets in other solar systems. We can estimate that too. We have our formulas that tell us what the force of gravity is, so hence we can work it out in places other than Earth. We have this constant because it's a function of the masses of the two objects. All right, quick calculation. A man has a mass of 85 kilos. Here's the information in table 1. That's just a list of these gravitational constants. Let's look at his weight on the Earth, the Moon, and Jupiter. Notice our formula there, force is mass times acceleration. That's Newton's second law. And we've just adapted it because the acceleration is gravity. And note that we're specifying the force is gravity there by putting the little subscript G in there. All right, you just plug your numbers in. Mass is 85, gravitational constant's 9.8. Put that in your calculator. 833 newtons is the force of gravity. And newtons is just our measurement of forces. Part B, the moon. Notice we've changed our subscript because it's not really gravity here on Earth. It's now your weight on the moon. And the constant on the moon is a lot less, 1.62, which gives you a weight a lot lower, 137. And the last one, Jupiter, has a lot more mass than Earth, hence 2,108 newtons. So obviously you have your weight that you feel like you're on Earth. On the moon, you weigh a lot less, hence you can jump a lot higher, things like that. But on Jupiter, it's far more massive, hence you feel like you weigh a lot more. There's some little extension questions there to challenge you. It's worth pausing the video, having a look at those, see if you can have a go at them. Okay, let's look at the forces on this object. We've got this box sitting on a table being attracted towards Earth. This picture on the left-hand side here is sort of a depiction of all the forces, and we sort of summarize it on the right-hand side there with that free body diagram. So the normal force, we've got it listed there a couple of times. We've got him listed in there and also in there. It's basically the idea of Newton's law of for every action there's an equal and opposite reaction, the third law. The object, the box, is pushing down or being attracted towards the table's pushing back. That's what the normal force is. Because the box is at rest, it's not moving, it's not accelerating in any direction, it's sitting there at rest. So because it's still being attracted towards the Earth, the table's holding it up, that's what we think of as the normal force. Okay, which force is the force on the box due to Earth? All right, what we're looking at here is this here, which is the force of gravity, or another way to say that is its weight. The paired force for that one is here. The box is being attracted towards the Earth due to gravity, but the Earth is also being attracted towards the box. We don't generally think of it in terms of the second way there, because the mass of the box is so insignificant compared to the mass of the Earth, but that's what's going on. That's the paired force. The box is attracted to Earth, just like the Earth is attracted to the box. So another name for the normal force we have over here. We have the force of the table pushing on the box and the force of the box pushing on the table. That's like the paired forces over there. Because the box is attracted to the Earth, the table happens to be in the way. It holds the box up to stop it accelerating towards the Earth. That's our paired forces there. That's the force of the table on the box, is another way of thinking about the normal force. And notice what we've got written over here. What conclusions can we make about the normal force and the force of gravity? Notice how I've written them there, slightly more correct in terms of the vector quantities. They're equal and opposite to each other, and that's what we've summarized here. They're basically like a negative version of each other. One acts up, the other acts down. Okay, 2 kilo box, that's important, that's a mass, rests on a horizontal table. That's actually important because it implies that the box is not slipping down an incline or anything like that. It's going to sit there at rest. So calculate the normal force. Before you do these calculations, always stop and have a think, what's the formula I'm going to need? We need that guy. All right, so there he is there, and you plug your numbers in. We know we need that one because the only information we're given is the mass of the object, and we're talking about a normal force, which is a force due to gravity. So hence we need a gravitational constant, and that's just a constant. And that's what we've worked out here. Now, the force of gravity is 19.6 newtons down, so the normal force is acting in the opposite direction, and we've depicted that as up. Here's the force there, there's the paired force on the other side there. Okay, now we did talk a lot about the weight, the normal force, the applied force, the friction. We didn't talk too much about tension. We're going to come back to that concept a bit more in the next sections, but it's essentially a force that's applied to an object, usually due to some sort of gravitational thing, is how we look at it in this area of physics. Okay, so do yourself a favour, have a go at the check your learning questions and look ahead at the next chapter before you try the next lesson. Thanks for coming.